All right, welcome back, everyone. Hope you all had a nice break. We are going to get started. So some announcements. Remember that advising begins today, so make sure you have an appointment with your advisor. Make sure you have everything you need for next term. The Achieve homework will be posted after class, and then I'm going to add questions for Chapter 16 after our class on Wednesday. I just want to see how far we get on Wednesday. But you will have the first 10 questions available today. And then that's due next Monday. And then next Friday, so in almost 2 weeks, but the end of next week, is the next unit exam. So this is unit exam 2. It is going to have 2 short answer questions, so I'll have a few more multiple choice. I'm thinking 18, and then 2 short answer. And then this will have the end of chapter 14, which is what was not on the midterm. So the Arrhenius equation is the first content in chapter 14 that wasn't on the midterm. So that will be on this assessment. All of chapter 15, which we'll finish on Wednesday, and then chapter 16 up to what we cover a week from today, so next Monday. All right? So keep that in mind. If y'all have any questions about things coming up. Okay, so it's been a while since we've been in class. But if you remember, the end of class the week before break, we talked about these ICE tables. ICE for initial change and equilibrium. And this is a way to calculate concentration of reactants and products at equilibrium. And the reason we need an ICE table is because for a reaction with reversible conditions, remember that if we're starting with some amount of reactants, they will react to form products. And those products are also reacting with each other to reform reactants. So at any given time, we have reactants and products present. Whereas in an irreversible reaction like combustion, you start with a certain amount of starting material. Once all of that is used up, there's no starting material left, and then you just have products. Well, that's not the case for equilibrium reactions. So ICE tables are for equilibrium reactions, because at any time we will have both reactants and products, and we are calculating the concentration or the partial pressures of reactants and products at equilibrium. So we went through this question here where we had H2 and I2, hydrogen gas, iodine gas, reacting to form HI. We were provided initial concentrations of the starting material. So we knew we started with 0.5 molar hydrogen and iodine, and it said in the question statement that at equilibrium we have 0.9 molar HI. So we know that if this is a reversible reaction, at equilibrium the H2 concentration and the I2 concentration are not 0. There's some other value. Because it's in equilibrium, we have both reactants and products present. So putting in everything we know from the question statement, that's in green. We start with 0 HI, but at equilibrium there's 0.9 molar, and then we start with 0.5 molar hydrogen and iodine. We also know that for the change row, we are going to decrease reactants because we're starting with only reactants. So the reaction must proceed to the right to reach equilibrium to have some products present. We're going to use up some reagents, and we're going to produce some products. So we use that X variable, but then we add the coefficient for any reactant or product in that change row. So we only have a coefficient here for HI. So we have the 2 there. Then we set initial concentration plus the change equal to equilibrium. Because we had all 3 values for HI, we can use that to solve for X. And then we go back over here, plug X in to solve for equilibrium concentration of H2, equilibrium concentration of I2. And now we know at equilibrium, this is the concentration of both reactants and the concentration of the product. Now we could calculate K at this time. Since we have equilibrium concentrations of everything, we could also calculate K. So this was the example that we did. This next slide summarizes how to set up an ICE table in general. So for a generic reaction, we have A and B forming C and D. First thing is while we set up the table, we always have initial, change, and equilibrium. That's how we get ICE or ICE. This will be in molarity or pressures if you're doing KP, so partial pressures. We'll do an example with that. Then across the top row, we have reactants and products. Spacing them out because we have more to write in the initial change in equilibrium rows. Then if you're given any initial concentrations or partial pressures, you put that in the first row. In the change row, we're going to use X or some variable, I choose X, to represent the change in moles from initial to equilibrium. So the change from initial to equilibrium. In the previous example, we had only reactants present at the initial state. So we knew that we were going to use up reactants to form products. But that's not always the case. To determine if we're going to form products or form reactants, if you're given initial concentrations of all four species, then you need to calculate Q. So remember, Q is same equation as K, concentration or partial pressure of products over concentration or partial pressure of reactants. So if you're given in a question statement concentrations for all four, or for all reactants and all products, Q, you need to calculate Q to see if you have a higher concentration of products at equilibrium, which means Q will be greater than K, which means the reaction will proceed to the left. We'll use up products and form reactants. Or if Q is less than K, that means you have more reactants than at equilibrium, and the reaction will proceed to the right. You'll use up reactants and form more products. So if more product is present, this means Q is greater than K for that first bullet point. Then the product will decrease. We'll have negative X here, and reactants will increase positive X for reactants. And then the opposite, if Q is less than K, then reaction proceeds to the right, adding product, subtracting reactant. But that does mean that for the change row, the change can be positive or negative, depends on Q. For reactants, it can be positive or negative, again, depends on Q for products. So in the change row, we will have either positive or negative. And then for A, it's the coefficient A times X. And then for reactant B, it's either positive or negative, coefficient B times X. For C, follow the same pattern, positive or negative, lowercase c times X, and then same for D. Then we'd add any known values that we have, initial concentrations or any equilibrium values that are provided, and then we can use I plus C, initial plus change, equals equilibrium to solve for X. Then we can apply X across columns. I'm just going to add an arrow here for this change row. Just remember that it depends on Q value compared to K, whether you'll have positive or negative. Okay, questions? We're going to do an example, but any questions at this point? Okay. Let's go to the next slide. So we are going to use an ICE table to solve for K for this reaction here. So we have SO3 decomposing into SO2 and O2 according to this reaction. We have 6.15 atmospheres of SO3. So now we're working in pressures and partial pressures. We'll be calculating Kp. Added to a vessel, kept at constant temperature and pressure, and then at equilibrium we have 0.31 atmospheres of SO3. Calculate the value of Kp for this reaction. Okay, so hopefully when you're reading this question or when you read it in the future, a few things will come to mind. The first is that we're at equilibrium and we are looking for K, which means we need to find equilibrium pressures, partial pressures. So let's remember that Kp is partial pressure of products over partial pressure of reactants. So we need to find, this is all at equilibrium. So we need to find the partial pressures of each species at equilibrium. We know one is provided, SO3 is provided, 0.31 atm. But we still need to find the partial pressure of SO2 and O2. So this is when we use the ICE table. So we will set up the ICE table. We always have, I'm going to abbreviate initial change and, actually I won't, I'll abbreviate in the next example. Here we'll have initial P in ATM. Then we have change. And then equilibrium. ICE tables will always have those 3 rows, and you'll always put the reaction across the top row. All right, I've done the setup for you here. Make sure you have that on your slide or on your page. And then now I'll give you a few minutes to try filling in as much as you can. So think about any information we have about initial pressures, any information we have about the change, and then anything we have about equilibrium. Okay, we are told 6.15 atm of SO3 is added to the vessel. Where does the 6.15 ATM of SO3 belong in the ice table? Initial for what? For SO3. So each species has its own column. Imagine it having its own column. If you need to write in lines, that's fine. But initial pressure of SO3 is 6.15. So we've got that filled out in our table. How about, let's see, what else do we have? We have 0.31 ATM of SO3 at equilibrium. So where does that belong? In the equilibrium row for SO3. Equilibrium pressure of SO3 is 0.31 ATM. That's almost everything that the question statement tells us. What other values can we add? Ignoring change, that row for now. We'll talk about change in a moment. What else can we add? Yeah.
0 for other two initials.
0 for the other two initials. How do we know that they're 0? Because nothing was added. Yeah, it doesn't tell us in the statement that there's any partial pressure for the products. So we can assume, unless it's asking for initial partial pressure, which I don't think you'll ever have a question of that, it says that 6.5 ATM of SO3 is added to a vessel. We can assume that's all that's added. So we have 0 product present at the beginning. We'll see another example where you're provided, I can't remember if it's pressures or concentrations, but the question statement has one of the two for each species in the reaction. So then you know initials is not 0, it's the value provided in the question statement. But we know it's 0 here because only SO3 is added. All right, now if we have 6.15 ATM of SO3, 0 SO2, 0 O2, which direction is the reaction going to proceed? To the product or to the reactant side? Are we going to form product or form reactant? We only have reactant present, so this is going to form product. It's not forming reactant. With the reactant here, the reaction will proceed to the right. We have 6.15 ATM of SO3, 0 product. This is an equilibrium reaction where we should have some reactant and some product present. So if we have 0 product present, the reaction is going to proceed to the right. That, thinking about which direction the reaction will proceed, helps us know which sign to use for change. We're going to be forming more product, then the X value here should be positive for the products. We're using up reactant, so the concentration changes. Negative for the reactant. It must be negative because we're setting initial and change equal to 0.31. So to go from 6.15 to 0.31, we have to remove some reactant. Okay, so with that, we have the signs for change. Now we just need X and any coefficient. We have a coefficient of 2 for SO3, so change is minus 2X. Coefficient of 2 for SO2, so change is plus 2X. And then coefficient of 1 for O2, so just X here. Now we need to find X. How can we do that? Yes. So we will say initial plus the change is equal to equilibrium. So exactly what you said, I'm just going to rearrange the equation slightly. We'll have 6.15 plus negative 2x, or in other words, minus 2x, equals 0.31. Subtracting 6.15 from both sides, we have negative 2x equals negative 5.84. dividing by -2, x equals 2.92. So if you have all values in one of these columns for any species, you can use that to find x. Here, we only have the equilibrium value for SO3, so we need to use this column to solve for x. And then now we can say 2x is the equilibrium concentration of SO2, and x is the equilibrium concentration of O2. You have a question?
No.
Okay. So now, at equilibrium, pressure of SO2 is 2x, which is 2 times 2.92, which is 5.84. And then pressure of oxygen is just x, which is 2.92. Okay, so these two values we get from the calculations here. We have equilibrium concentrations or partial pressures of everything. We're not done yet because the question asked for K. So we need to go back to the equation for K and plug in our known values. So Kp, partial pressure of each product raised to the power of its coefficient. So partial pressure of SO2 squared times partial pressure of O2 divided by partial pressure of SO3 squared. Plugging in values, we have 5.84. Squared times 2.92 divided by 0.31 squared. So this is equal to 1036. That is the Kp value for this reaction. Does this reaction lie to the right or to the left? I'm seeing some thumbs. I hear a right. Other ideas? I need more of you to tell me. Does it lie to the right or to the left? More. Right. Okay, yes, it lies to the right. We have a very large K value. That means that at equilibrium, we have a much higher partial pressure of the products than the reactants. So it lies to the right. On the right side of the reaction equation appears the products. Oops. So this reaction lies to the right. Okay, questions on this? We're going to do another ice table that's even more involved. Yes? No. Oh, okay. So we know that at equilibrium, the reaction lies to the right because the Kp value is greater than 1. Q is a different question. So the Q is at a given time, will the reaction proceed to the right to reach equilibrium or to the left to reach equilibrium? All right. We're going to calculate Q in this next problem. So this is a big one. We have 2 slides for this one. Buckle in. I wish I could say it's going to be fun, but it might not be. I'll try though. Okay, so we have another reaction. We have BrCl forming bromine gas and chlorine gas. BrCl decomposes into those two gases. We have a sealed container with 1.75 atm. We're talking about partial pressure, so we'll be using Kp. So we have 1.75 atm of the reactant, and then 0.75 atm of bromine, 1.15 atm of chlorine. So we are given partial pressures of each species. This is a problem where we need to calculate Q. We need to determine at this time, will the reaction proceed to the right to form products and use up reactants, or will it proceed to the left to form reactants and use up products? We'll have to do that first, then we'll do a bunch of calculations to calculate partial pressures of all three gases at equilibrium. So there will be some shift to reach equilibrium. We'll use that shift to calculate the partial pressures at equilibrium. All right. So we don't know, again, like I said, if the reaction will proceed to the left or to the right based on this information. So our first step is to calculate QP. And remember, this is the same formula as Kp. So we have pressure of Br2, pressure of Cl2, divided by pressure of BrCl, and we square that because of the coefficient in the reaction. And then we plug in values. So Br2, 0.750 atm, Cl2, 1.15, BrCl, 1.75 squared. And then this value is 0.282.
I know that P and KP are different values, but why couldn't we use KP to see where it lies?
We are about to use Kp. But as you can see from this equation, the Q is not equal to K. So at equilibrium, the ratio of products over reactants is 32. But right now, the ratio is 0.282. So that tells us now, will this reaction form more products or will it form more reactants to reach a Q value equal to K? Okay, so on that note, with Q being 0.282 and K 32, Q is less than K. Remember, Q and K are both products over reactants. So will the reaction proceed to the right to form more products and reach equilibrium, or to the left to form more reactants to reach equilibrium? I hear some different answers, so let's talk about it a little more. Q and K are both product over reactant. At equilibrium, the ratio of product to reactant is 32. So that's greater than 1. That's a high partial pressure of products compared to reactants. Right now, it's at 0.282. That's a low partial pressure of products. So to reach 32, we need more products to be formed. And reactions always tend toward equilibrium. So it'll always tend toward the Q value being equal to K. So with Q less than K, the reaction will proceed to the right to form more products. Now we do all of that, calculating Q, to know which signs to include for the change row in the ICE table. The next step is to set up the ICE table. We know that we are going to form more products, so we should have positive X for the products in the ICE table. So step 2 is the ICE table, and then here I'll abbreviate both, or all rows are in ATM, but we'll just have I for initial, C for change, and E for equilibrium. Same setup, and then we've got the reaction, reagents and products across the top row. Now we're given partial pressures of the reactant and both products. All of that information goes in the initial row. So the initial, meaning when we measure the partial pressures, that pressure of BRCl is 1.75 atm. BR2, 0.75. And Cl2, 1.15. All of that goes in the initial. That's not at equilibrium. We need to calculate equilibrium, and then we'll think about how to set up that change row now. Okay, for change of BRCl, what do you all think? What should I put here? Minus 2x. Why minus 2x? Someone else. Why is it minus 2x here?
Proceed to the right.
It'll proceed to the right, so that means we're using up BRCl. We're going to say something different. And then why 2? 2 moles. That's the coefficient here in the balanced reaction equation. So we're using up reactant. We're using up BRCl. Has a coefficient of 2, so we have minus 2x. That means on the product side, we're forming products, so we should have both positive. And they're both just 1x because bromine has a coefficient of 1, chlorine has a coefficient of 1. Okay, now what? We don't have any equilibrium partial pressures for any reactant or product. So what can we do now to find equilibrium? Would we be able to set them equal to each other? So what would you set equal?
Use BRCl and BR2.
But at equilibrium, those concentrations might not be equal to each other. They can have different concentrations at equilibrium. We will be setting up an equation, but slightly different than that. What else do we know about equilibrium? Not in the table, but in the question statement. What'd you say? Is at 500 Kelvin. What else do we know? They're all gases. There's more. Kp. Yes, we're going to use Kp. So the ratio of the equilibrium partial pressures of Br2 and Cl2 with the denominator equilibrium partial pressure BRCl, that's equal to 32, equal to the Kp value. So we're going to set up a Kp expression using X values. So at equilibrium, the concentration of BRCl is 1.75 minus 2x. Sorry, the partial pressure, not the concentration. So we're going to keep X in those equilibrium partial pressures. So 1.75 minus 2x for BRCL, 0.75 plus x for BR2, and 1.15 plus x for CL2. Now we'll plug this into our Kp equation. So step 3 is to use K to solve for X. So Kp, pressure of products over pressure of reactant squared. And now we're putting in this entire factor for partial pressure of BR2 that is equal to 0.75 plus x. Partial pressure of CL2, 1.15 plus x, and then that expression over there for BRCL. So we're putting in that whole factor into the K equation, and all of this is equal to 32. So BR2, 0.75 plus x, CL2, 1.15 plus x, and then BRCL is 1.75 minus 2x, and that whole thing squared, but instead of putting the exponent here, I'm going to multiply, or just put another factor here. So multiplied by 1.75 minus 2x. This is just in preparation of what we are about to do to simplify. All right. Now we have to multiply these two factors together. Y'all remember how to do that? Thinking back to algebra. So one student in my earlier section said we distribute, which that's exactly what we do. So you do 0.75 times 1.15 plus 0.75 times x plus x times 1.15 plus x times x. If you just remember it that way, that's fine. When I was in algebra in high school, my teacher taught me FOIL, the FOIL method. Some of you learned that, a few of you. So FOIL is the same thing. F first, O for outside, I for inside, L for last. So we use multiply the two first values, then the two outside values, then the two inside values, then the two last values. So same thing. So we will do that for the numerator and the denominator. 0.75 times 1.15, 0.8625. 0.75 times x is just 0.75x. 1.15 times x, and then x squared. We'll do the same thing for the denominator. So first, 1.75 times 1.75. Outside is 1.75 times negative 2x. Inside is the same thing. And then negative 2x times negative 2x is 4x squared. Remember, all that's equal to 32. I'm going to do one more step to combine like terms, and then we're going to go to the next page for more room. In the numerator, we have a value without any x. We have two values multiplied by x. These two we can combine, and then the x squared has to stay separate. Then same thing with the numerator. This value stays as it is. We can combine the 3.5x, and then 4x squared stays as it is. So a bit more this way. Combine like terms, we have 0.8625 plus 1.90x. So that's the term that is different now. We just combined like terms, plus x squared. And then the denominator, 3.0625 minus 7x plus 4x squared. So the 7x is the combined term. And then this is all equal to 32. Now we'll move to the next page. I'll rewrite this expression right here on the next page. So let's remember what is our goal. So we've got a lot of steps to do, but we gotta keep in mind what we're trying to solve here. We're looking for the partial pressures of each component at equilibrium. And at equilibrium, we need to know what x is to find that partial pressure. So we're going to solve this equation. So we have one variable equal to 32. And we'll have to solve this to find the value of x. Then we can plug it back into this equation.
Where did you get the 0.8625 from?
That was the 1.15 times 0.75, the first. All right, I will move to the next page, but just rewrite that. So we have okay, so that is just the same thing that we have on the previous slide. And then let's write down the goal here, which is to solve for x. Now, if we have an equation with an x and an x squared, do you remember how to solve for the x value? The quadratic formula. We're going to have to use the quadratic formula. Remember from algebra, and then we'll be able to solve for x using the quadratic formula. But to first use, before we can use that, we need to set or get this expression into an ax squared plus bx plus c equals 0 format. And then we can use quadratic formula. Okay, so we have this fraction on the left side. We need to not have a fraction. So we're going to multiply both sides by that entire denominator. It will cancel out on the left. So we'll just have the numerator. This is equal to 32 times that denominator, 3.0625 minus 7x plus 4x squared. Now we distribute the 32 on the right side. We'll do 32 times each of those terms on the right side. The left side still stays the same. So 32 times 3.0625 is 98. 32 times negative 7x, or negative 7x is 224x. And then 32 times 4x squared is 128x squared. Now we have no fraction, which is good. We need to shift locations of everything so that all of the combined terms are on one side of the equation and the other side is just 0. That will be the ax squared plus bx plus c format. To keep the x squared term positive, I'm going to subtract the left side from the right side. So I'm moving everything over to the right. We'll subtract 0.8625 from 98. We'll subtract 1.90x. We'll subtract x squared. We're really doing that from both sides, but I just wrote it on the right side. So the left side will be equal to 0. Right side is 97.13 minus 225.9x minus 127x squared. So now we have our, oh, this should be plus. Now we have our a x squared plus bx plus c format. I'm going to just rearrange the order of these so that the x squared is first, and then the value times x, and then the value without an x term. So 127x squared minus 225.9x plus 97.13. So in this format, 127 is A, 225.9 is B, 97.13 is C. And those three letters are used in the quadratic formula. So we need to identify A, B, and C in this format where we have x squared x and then a value without an x. Then we use quadratic formula. All right, so we used K to arrange this equation. Now we're going to use the quadratic formula to solve for x. Quadratic formula. I'll write this out for you if you don't remember. So this is, again, a way to solve for x once you have the ax squared bx plus c. X is opposite sign of your b value plus or minus the square root of b value squared minus 4 times a times c divided by 2a. So now that we know A, B, and C, we can plug that into the quadratic formula. So B in our equation here is negative 225.9. I'm going to round that up to 226. Here we have negative B, really the opposite sign. So in the quadratic formula, it's positive. A is 127. C is 97. I'll round to 97 here. And then we divide by 2 times 127. Then simplifying, x is 226 plus or minus 40.9 divided by 224. When you use a quadratic formula, you're going to get always two x values. So we have 226 plus 40.9 divided by 224 and 226 minus 40.9 divided by 224. We're going to have two values, and then we have to go back to our ICE table and think about which one makes sense. So I'll write the two values here. So we're almost done. Well, we're done with the quadratic formula. We're going to identify which of these two values make sense for this reaction, and then calculate equilibrium concentrations. We'll do all that on Wednesday since we're past time. So we'll finish this, and we'll finish chapter 15 on Wednesday. Hi. Once
earlier on how you